So I have to start, right? All right, I'll get started. All right, so today we're going to do ATP synthesis and equilibrium. I'm going to go over some of the molecular mechanisms of ATP synthesis really quickly, because I know some of you have been acquainted with it in the past. I'll just tell you some of the biophysical approaches and some of the biophysical considerations, because it's going to filter into our talk of chemical potentials. If you were partying hard on spring break and weren't here on Monday, I have your exams. If you want to take them off, they hang back. There is homework 4 on Blackboard, and it's due a week from today. It's really, really quick. The caveat for homework 4 is one of the questions you may want to hold back, and it actually says it on the question you may want to hold off until after lecture on Monday. So it's up to you, but it's an equilibrium question, equilibrium PKA question. We'll talk about it in more depth on Monday. All right, so any questions? All right, okay, so we talked the other day that we synthesize an extraordinary amount of ATP. And we said, okay, well, that's about 70 kilos per day, 150 pounds. That's an amazing amount. It is a problem for equilibrium, and as well as energetics. So think of how we do that. So a lot of you, well, probably all of you, are acquainted with this, this big protein machinery called ATPase. It is built out of 2 main units. It's FO, an F1 unit, and I just wanted to introduce a little bit, reintroduce it, and some of the considerations. Right, so it's a molecular motor that is fundamental. So here it is in terms of the subunit composition. There is a portion of it, it's alpha beta subunit that extends to the cytosolic medium, and then there's this transmembrane component. The critical thing is we have, if we said, okay, if we metabolize ATP, what is that energetically? Is it negative or positive energetically if I metabolize it? All right, get energy out of it, right? So it should be negative. So if I have to synthesize it, right, it's a problem because it's positive, right? Formally, I'm doing the reaction in reverse, right? It's plus 30 kilojoules of all that. So we've got to couple it to something. And so what we said last class, even in dealing with, okay, how do I use ATP to drive unfavorable reactions? The same applies to synthesizing ATP. I have to couple it to something energetically more favorable than what I require. So, and the critical thing here is coupling it all to the movement of protons down a concentration gradient. And that's really how this system works. Is I need to get some work into the system in order to drive this thing, and I do it with protons. Now, the protons aren't just simple leakage across the membrane. They are coordinated and orchestrated type way. So here's the general issue with equilibria. We said, okay, if I'm dealing with the hydrolysis of ATP to ADP and inorganic phosphate, and I want to set up an equilibrium constant for that, that's ADP times inorganic phosphate concentration over ATP concentration. So if I want to run this in reverse, I have to think about how I would do that. So if I want to run this in reverse, where would I poise ADP and PI? High or low? That's a good question, right? So I want to run this thing in reverse. So think about the equilibrium, how that equilibrium, right, is now opposite of this one. And so I have to think about what would poise it to the left and right. So remember their internal check when you keep doing these problems, make sure that the K values actually make sense of whether it's energetically favorable or disfavorable. All right, so if I want to establish a large concentration gradient of ADP and PI, that's essentially what I want to do to run this thing in reverse, right? But that's not intrinsically easy given that minus 30 kilojoules per mole going to the right. So there's a way to do that. And the way to do that is, this idea of coupling it with protons. So this is generally how we get around that problem. So I'm going to use this. Notation a lot, especially when we're doing some molecular recognition. When I have a big dot like here, that denotes a complex. So in this particular scenario, F is a protein, is the ATPase itself. So here's a general equilibrium of ADP and inorganic phosphate making a complex with F, which is the ATPase. And then that is going in some equilibrium to ATP and F star. So that's the product of the reaction, that's ATP synthesis, and F star is just some new conformation of protein F. All right. So basically what this equation is describing, it's describing a binding reaction, and it's describing a binding reaction in such a way that at the end of the day results in ATP formation. That's the critical thing of that. Now, note I've actually drawn the arrows in an appropriate way that are going way to the left. Because we know, right, this would be normally, if I don't couple this to anything, this would be about plus 30 kilojoules per mole. The opposite, basically the negative what the hydrolysis reaction is. So equilibrium is clearly going to lie to the left. So how do I drive it to the right? All right, well, the key to driving it to the right is to basically write the same equation, but now involve protons into the equation. All right, so here's where protons come in, and basically this is the same equation. I still have F, I still have some conformational change going to F star, but now I have the binding of protons in this equilibrium. All right, so if I write the equilibrium constant, if I write KQ, how would I write that for an equation? Just generically. Products divided by reaction, or in this particular case, ATP S star H plus over this times this. All right, so mathematically, right, I could think of, all right, well, what would happen to the equilibrium constant if I change the concentration of protons? So that's the critical thing here, is changing the formal formula of the equilibrium constant in such a way that I can drive things to the right or left. Right? That's the whole, mathematically, the deal with what I do with the protons.
So dot means that on this side, all of it is one complex.
The dot means, so the dot means that in the ATPase formally, that's what F is, protons are in it.
In the complex of ATP.
In the complex of the ATP. So this is the product of the reaction. Now ultimately the ATP is just going to drive protons across and it's going to release. But before it does that, there is a complex with protons. All right, so ultimately this is it's simplistic before the whole, the mechanistic detail comes in. All right, so I start with my F ATPase bound to ADP, my substrate essentially, inorganic phosphate, and I have protons. All right, at the first step, I'm going to make a complex with the protons, and you see one of these protons kind of in white is actually bound. Now this is at very, very low, actually no real molecular resolution to this. And then ultimately, I'm going to couple the movement of a proton down the concentration gradient. And if it goes down the concentration gradient, is that energetically favorable or disfavorable? Favorable, right? When we think of diffusion, right? That's the favorable reaction. We'll talk about chemical potentials more. And then ultimately, if I release that, so I'm coupling something energetically unfavorable, which is ATP synthesis, to something favorable, which is moving protons across. It's a general theme all across bioenergetics. Actually, I will show you that. All right, so this is mitochondrial use of protons. And so this is what's often called, I don't know if you guys have you heard proton motive force before? You have, okay. So you know the proton motive force, you know all these components of the electron transfer chain, you probably had to memorize them at some point. There's lots of little cofactors involved. BC1 complex, cytochrome oxidase. And ultimately, this whole thing is coupled to ATP synthesis at the end of the day. At each of these steps, note that we have the delivery of protons across the membrane. All right, this is really helpful because ultimately this creates a proton concentration gradient that ATPase can use to drive synthesis. All right, so and that's really the key to the electron transport chain. So you might ask the question, okay, well, why why have all these steps and all these components and all these redox factors, cofactors? Well, the real deal is, I need to deliver protons across the membrane, and that's the way to do it ultimately through this complex. All right, so we know that the proton motive force has delta G associated with it, right? That's the critical thing. If I want to drive an unfavorable reaction, I need to give delta G from somewhere, negative delta G from somewhere, and it's coming from protons. So the way to think about it, any proton pump, right, is, I might have hydroxide on one side, I deliver a proton from, in this case, an N side to a P side. And that's essentially done by any of these components of the electron transport. So mathematically, how much do I get out? And we'll talk about this in more detail today, certainly the upper part of it. So if I think of the proton motive force, there's a chemical contribution to it, and then there's also this electrical contribution to it. The chemical contribution would apply not only to protons, but any system where you have transport from vectorial transport across a membrane. So, any transporter is going to operate on this. So if I want to think of just calculating the chemical potential of this, and we'll look at the derivation a little bit today, I can think of a delta G chemical of just being nRT and then the ln of the concentration gradient. So ratio of how many protons are inside versus how many protons, what's the proton concentration outside. All right, so that's one component to it. There's actually a second one that we often ignore, which is this idea of membrane potentials. And we associate this with the Greek letters on the side, and that's my membrane. Because we all know that, okay, there is this differential charge across the membrane. And certainly if I deliver protons on one side versus the other, I have a differential charge. So if I want to calculate this now becomes more of an electrical term. The difference would be the potential inside versus potential outside. And I could use the same types of equations that I use in physics in dealing with electricity to figure out a delta G. So delta G is just gonna scale to the charge in the molecule, in this case +1 for a proton. F is the Faraday constant, we can ignore it for now until we talk about electrical potentials. But it is some scalar volts to a real delta G term. And then that scale volts. So there's two real roles of the protons here. Both of them give favorable delta Gs, but one is coming from the gradient and one is coming from electrical. Okay, so so that's the deal, right? With all of these components of the electron transport chain, and so these are often called complexes 1 through 4, the electron transfer chain. So these are all driving protons onto one side of the membrane, and then ultimately that establishes a differential membrane charge, and also establishes its chemical potential to be able to use protons. All right, so the key to ATPase, or the thought, right, is that, okay, well, the way to drive synthesis is simply with protons. And so this was a really, really elegant experiment that someone probed a long time ago. And so what they did, there's a way to actually isolate mitochondria from cells. You can actually lyse cells open, you keep mitochondria intact, and then you can use differential centrifugation to just get the mitochondria. And the mitochondria is really what you want, right? In terms of if you want to study ATPase, you can get rid of all these other cellular components. So what someone did was isolate the mitochondria. They raise it to a given pH 9, and they basically put this in more or less pure water, right? So really, really unbuffered solution. And then they add a chemical called linomycin. What the linomycin does is actually punches holes in the membrane. So basically, what it will do is collapses any potassium gradient. And then they can just add basically protons to it to poise outside versus inside. So basically, if you do that and you collapse the potassium gradient and poise the pH, you can jump the outside proton concentration. All right, so even just this simple thing, I've just added a couple chemicals, I've just added protons to the system. This actually resulted in the generation of ATP. So this is the linkage, the experimental linkage from protons to protons being really important in ATP synthesis. I mean, clever experiment. So, so the whole, fundamental deal with the proton motive force is it has this pH component, outside versus inside. It also has this membrane potential component, or delta psi. And all that is being used ultimately to drive the F1 synthesis. The question is, how much do you need, right? And how much energy do I get out of this ultimately? So I can calculate it, right? I can calculate the pH difference from the outside to the inside compartments. That's usually calculated about 80 millivolts. And with any of these, a useful way to convert energy, right, is into, millivolts is kind of awkward. We can actually do this in terms of the Boltzmann, in terms of kVt. So if I do this, and I can show you how to do this later, I can convert the energy contribution of the pH difference of being about 3 kVts. I can, I also have this membrane potential component to the delta G, and that's about 6 kVts. All right, so ultimately I get about 9 kVts per proton if I want to scale it that way. I also know I can also convert minus 30 kilojoules per mole, which is ATP hydrolysis, or plus 30 kilojoules per mole, also into kVts, and that's about 20 kVts. And so if I think about it per proton, right, in order to get my 20 kVts, I need at least, probably close to 3 protons to do it. It takes 3 protons. Energetically, it takes 3 protons to get the system moving in order to get the energy I need to drive these. All right, so where do 3 protons come from? Well, at the molecular level, this is what's known. Paul Boyer, who's the person that first coined this mechanism. This is called the binding change mechanism, where I have rotation of 3 subunits that are attached to each other. Ultimately, to couple the synthesis of ADP and PI into ATP. If you want to know the price of it. So there's 3 catalytic sites, and energetically that makes sense because I need 3 protons involved in the process in order to get 1 ATP out. So in the molecular view, it makes sense to the energetic view. And so these things attach to it, and at this point it's just kind of how this goes. But it's basically a rotation that's driven by a flow of protons through the F naught subunit of ATP. So that's ATPase in a nutshell. Now, so this is a molecular motor, it has to move. And the cool thing experimentally is, well, how do you prove movement of something so small as a motor protein? And so what we saw last class was this use of optical tweezers to look at kinesin moving across and transporting vesicles across microtubules. You could use a different technique, and this is a really clever one. If I want to visualize this thing spinning, the FO subunit spinning, you can actually attach a long filament to it. So you can attach biosynthetically an actin filament by use of this avidin linker, which is going to attach to a strip avidin. Because you can't watch this thing rotating itself, so basically you're attaching a propeller to it. So you can see this movement. All right, so what did I show you? The pictures are really cool. So this is actually watching spinning of the F1 ATPase. That's basically looking at this actin filament and looking down on it. So if this thing spins, right, I should see the actin filament go in different orientations. And you can actually do that. So here it is in terms of the pictures, and you can basically see how this thing is rotating. You can get angles out of it, you can get speed out of it. And you can actually couple the number of revolutions as a function of time, which to me, I think is a really cool thing. So here's the sequential images of fulfillment. So that's really the thing that I want to talk about ATPase. The big lesson from ATPase is there is chemical work, and then there's free energy that you can get out of chemical work. Ultimately, much like the movement of protons, you can think generically in terms of the number of moles of anything changing. So in this particular case, right, this is import of some molecules within a cell, and basically what I'm doing is going from a number of moles n to a number of moles n plus delta n. That is free energy, and that free energy scales to the difference of what we call mu, or chemical potential, times the change in the number of molecules, external and internal. So we'll look at how to calculate that and where that comes from. All right, so this is how to think of the chemical potential. I can think of the chemical potential of mu of any particular species. I'm just going to call it sub I as scaling to a delta G over some total number of molecules, or delta Ni. And so in this particular expression, I'm thinking of a free energy for one single molecule, which is really awkward, right? You never do things in terms of per molecule. But if I were to think about the units of this, right, there's a free energy, so some kind of joule over some number of molecules. Awkward, right? All right, so we usually don't do that, right? We do things in terms of concentrations. All right, but generically, if I'm thinking of a discrete number of water molecules, a discrete number of solute molecules, here is, at time 1, this is going towards equilibrium. So the big thing to note, right, is what is happening to the concentration gradient. So basically, the concentration gradient is changing in such a way as the molecules are going from internal to outer, that hopefully, at the end of the day, how many should be inside and how many should be outside, if I'm at equilibrium? Should be pretty similar to each other, right? That would be the equilibrium situation. I guess I could, if I wanted this by time, count each of these, and they should be roughly equal to each other. All right, so that's the equilibrium. So that would be a spontaneous transition, right? I don't need any active transform. You don't need to expend any energy because I'm going down the concentration. All right, so if I think about it in terms of what's happening at equilibrium. So basically we said, okay, well, what happens at equilibrium, we're just going to set at a delta G of equal to 0. All right, so I can think of this in terms of the number of molecules. So everything's going to scale to the chemical potential and then the number of molecules. So I can think of it as the chemical potential inside, let's say inside the cell, times the number of molecules in, plus the chemical potential outside of the cell, times the number of molecules in the outside. And I'll set the whole thing equals to 0. All right, so one thing we can say is we just have one set of molecules. In this particular diagram, they're just these blue things. I don't know, call them what you want, glucose, for example. So I'm going to really confidently say this, that they're coupled movements. So why do I so confidently say that the number of molecules changing going in is equal to the number negative back out? It's a closed system. So if I move something from out to in, it's the negative if I'm dealing with out, in to out. All right, pictorially, what's happening? This is a good way. Okay, so I've just made one red, right? If I'm thinking about the change in the number of molecules, right? If I lose one to the outside, I'm going to gain one on the outside. So that's what this does. Which makes sense, right? If I'm at 50 here and I go to 49 and I'm at 5, right? I'm going to go to 6. I coupled movement. So if I increase the number outside, I'm going to decrease the number, which is pretty simple. All right, so mathematically, this is a really helpful tool for me. All right, and again, it's a simplification because there's only one set of molecules. that's all right. We just care about glucose in this variation. So, so I have this as my starting equation, but I know, right, basically delta NN equals minus delta NL. All right, so what do I do with that? Well, I mean, I can just do a easy substitution. All right, so what that does for me is it puts everything in units of in, instead of having n in and n out because everything's coupled. All right, again, everything's equal to 0 because I'm at equilibrium. What this gives me is a simple rearrangement from here where I can just take delta n in and move it outside. This is what I've done here. And then I have the chemical potential difference of inside versus outside. All right, so if I'm at equilibrium, here's my final equation. What does that mean for mu in and mu out? I think I heard it, but I'm not sure. They should be equal to each other, right? Because this is a concrete term, right? This has to be a non-zero number. I have real movement. Let's assume. All right, these should be equal to each other in order for that whole thing to be set to 0. So that's the beauty of this mathematical rearrangement, because it now tells us something about the chemical potentials. So at equilibrium, right, mu in is basically going to be equal to mu out. All right, so that's here, right? Mu in is equal to mu out. So if a system's not in equilibrium, right, my delta G is no longer set equal to 0, and now I can think about concrete situations. All right, so in order for, for example, for delta G to be lower than 0, what does that mean for mu in versus mu out? They're not equal to each other, and which one's got to be bigger? Yeah, so mu out should be bigger, right, to make this a negative term. All right, so there's some physical meaning in that, and then I can think of situations which n decreases spontaneously, right, and that signs would be opposite to each other. All right, so it gives some meaning. So we said last class to ignore water in a lot of cases. And we said, okay, well, typically what we think of when setting up these equations is what we call an ideal dilute solution. This is a pretty, well, is this a valid assumption? I'm just going to say that the assumption is pretty good. The concentration of water in a cell, large, right? Probably pure water, about 55 molar. It's a little bit less than that. If I think of where protein, ATP, and things like that are poised, what concentration regime am I in? What do we think for ATP? It's not molar, by the way. It's not going to be more than molar either. So it's going to be on the couple millimolar scale. All right, so what we're going to see today is where I poise ATP, TI, things like that is actually going to control the amount of free energy I get out. So we're going to see in a second this assumption of ideal dilute solutions really, really handy for us. Because I don't really care about things in terms of individual molecules. In many cases, I'm interested in things in concentrations. All right, so here's basically an ideal dilute solution. Here's my solution. My water molecules are basically blue. I'm not drawing 55 molar, but there's a lot of them, right? And I'm going to add some solute molecules to it. By the dilute part, what that means energetically is there aren't many solute molecules. All right. So what that means is if I keep adding more solute, if I'm transporting glucose across the cell, whatever, I never reach a concentration where these interact with each other. There's not many of them. All right, from a concentration point of view. So I don't care about what happens with energy if I just change numbers. If I have 5 or 6 or 7 on the right, I don't care. They're not interacting with each other to suddenly get more energy out. All right, so this is hopefully not too dense. So this is basically how to think about chemical potentials and concentrations. All right, so in this case, here are just two regions. If you want to think about it as the inside of the cell, outside of the cell, or side of the plasma, whatever space you want for plasma space, that would work. So basically, I have two different regions. All right, I'm going to use my favorite kind of grid box type analogy to think about it. All right, so blue is solvent, basically just kind of water molecules. Red is solute, so I don't know, glucose is still fine. And I can see that the numbers have changed from some region inside of the cell to outside of the cell, right? The solvent really hasn't changed very much. It's the solute that I'm really interested in. The solvent's just set at some high threshold. So this is one way to think about it. Once I start thinking about it this way, then I can use kind of my favorite, my favorite multiplicity entropy type equations. All right. So this is a situation in an ideal dilute solution. Now I said, all right, well, I don't like thinking of things as kind of pure numbers of molecules. It's especially awkward, right, when I'm dealing with high solvent concentrations. So if I want to think of the difference in chemical potential, I might think of, region 2, region 1, which might be outside, inside the cell, as being RT, ln, and then just some concentration in region 2, region 1. All right, so this is the final equation, and basically this is just a way to go from numbers, awkward, to real concentration terms that we're more accustomed to using.
So all ideal solution means is that the molecules aren't interacting with each other.
Correct. That basically any solute that I'm dealing with is such low concentration compared to the solvent, and there's not much of it. So in terms of, if you want to think spatially, right, they're usually spaced far apart from each other so they don't interact with each other. It's an assumption, yes, but for most situations it's going to hold. Definitely the situations we deal with is going to hold. So whether I have 20 millimolar or 5 millimolar glucose, the energy of the glucose isn't going to go up with that. So that means everything it becomes concentration differences. So, all right, so mathematically, I can think of the difference in chemical potential as scaling to, if I do want to do individual numbers, which is where this all starts from, it's some entropy term over some number of molecules. So all of what you learned from positional entropy and dealing with these types of systems applies. But where it starts is in terms of numbers of molecules. But everything is still minus TPS scaled over some number of molecules. All right, so this is a little bit awkward, but we can think about the types of equations to convert this into something like this. All right, well, there are a couple ways to think about it, right? We dealt with entropy a good amount, right? And I know that, all right, if I want to deal with it in a statistical definition, my entropy scales to some number of molecules, pi, ln, pi. I could think of, this type of system in terms of energy levels. I know, I have some number of molecules at P0, P1, P2. I know in order to get probability, right, I just take the number of molecules in a particular level and I just divide it by all of them, and then I should get some probability. Once I have that, right, I just substitute that into PIs, and then I scale that to the number of molecules, I can get an entropy out of it. All right, so that's one useful way to think about it. So, another simple way to think about it, right, is with some positional terms instead. And we've learned how to deal with this because we know in this particular situation, I'm going to deal with M as, what is M in this case? Yes, numerically, if I have this grid box system, what is it? You guys have done this probably. No, yeah, 16, right? It's just the number of oxygen. All right, and then I could think of each of the solute and the solvent in different ways too. All right, so remember that at some point you had a question with different types of molecules within a grid box system. that's what this would kind of look like. But thinking about it in terms of, hey, there's solute molecules, there's water molecules, and hey, there's some glucose molecules. You could think about the system the same way. All right, so here's that way to think about it, right? I could have, and I've just put this at discrete energy levels and just kind of made up. Here are all the empty grid boxes. Here are, you know, here's my solvent molecules in energy level 1. Here's my solute in energy level 2. And it doesn't matter, right? That's relatively arbitrary, but I could think about how to use, you know, these types of equations to think about ideal solutions. So if I think about the probabilities here, right? My probabilities of having empty, you know, or let's say having solute will be this over the total, and then same thing with my solvent, and then same thing with my empty boxes at energy level 0. So this is just a way to go, this is just a mathematical trick to go from something like this to something like this. All right, so if I do that, basically what I get out of it, right, I might have an entropy in one region, and then basically I'm using the statistical version of entropy. All right, so if I do that, I can combine and I get something that looks like this. So all I care about is what's in the Ln terms. All right, so it's just some number of molecules over the total, you know, number of boxes in region 2 minus that in 1. So if I just look at it, right, I think of what that term means. Well, it's some number of molecules over the entire size of the system. All right, that's concentration ultimately, right? You know, some number of solute over size of the system. So that just scales the concentration. So ultimately out of it, that's where the concentration terms come in. So this would be C2, this would be C1, and I can just collapse that thing into one element. So if I want to think about it in terms of KBT, it's just KBT ln of concentration in region 2 over region 1. So that's where the derivation comes in. All right, so chemical potentials are usually calibrated with some reference standard concentration. If I want to do that, that's just C2 over C1, and then very often I will have a standard potential. So every time I have a standard chemical potential, I just give mu naught, and all I've done is calibrate it with some known concentration, or some standard concentration, CO. So the thing to note from today's lecture, especially as we go forward, there will be standard conditions, and then there will be sort of non-standard conditions. That'll be interesting. All right, so if I want, right, I can go from a standard to a non-standard if I know how these things relate. So chemical potentials, if I'm at equilibrium, everything balances out, right? My delta G is equal to 0. I could think of any reaction that I want to, and you know, and things should be poised, you know, things should be all equal in terms of the products if I'm at equilibrium. So the n terms that I put in front of everything, these are just stoichiometric terms. So I don't have to have 1a, 1b, but it could be 2, it could be 3, it could be whatever I want. The variable that I'm going to use today is zeta, and that's just going to track my reaction progress. So we saw reaction